0, so get pi r squared. Done. Isn't that nice?
Sorry, another one? Is there another one for the circle?
This is the best one. This is the easiest one. Polar coordinates are made for circles. It makes life with things that are circles easy.
So what's the R if it's not a circle?
What do you mean? Oh, I'm going to do another example. Here we go. Find the area enclosed by one loop of a 4-petal rose, r equals 3 cosine 2 theta. All right, so this is the 4-petal rose. I don't think my mom will like it if I give her that, like a picture of that equation for Mother's Day this year. No?
No.
Should I make it cosine 4 theta, make it like an 8-petal rose? No? She won't. I don't think she'll appreciate that. No. All right, so we need to, understand what this was again. Okay, so we did this earlier. It drew like this, remember? And it did this, then down, right? This thing? Yeah. Something like that, something like that, something like that, something like that, right? Now, that's terrible. When it did this, do you recall the angles that it did this at?
Yes.
Yeah? So I want just one petal. We just talked about we could do this half, right? And double it. Or we could go like this bottom half. So what do y'all want to do? Start from 0 to go to pi over 4, or you want to go from pi over 4 to 3 pi over 4? 0 to pi over 4? And double it, right? So it should be twice the integral from 0 to pi over 4 of half of the radius 3 cosine 2 theta, but what? Squared d theta. And the 2.5 cancel, right? I square this, 9 comes out, and I have cosine squared 2 theta, right? D theta. And you know how to integrate that, right? Half angle equals dot, dot, dot. I'm not going to take that the rest of the way, but you know what to do with that? That's a pretty simple integral to get something pretty complicated, right? To find that area. Turns out to be a pretty relatively easy. There's no like trig sub or anything crazy we have to do with that. It's pretty straightforward. When I use the half angle, the power is going to come down. I'm going to get like 1/2 plus 1/2 or something like that. Remember that formula? What's going to be in the new trig function? Cosine what? 4 theta. Just you'd have to be careful with that. Because you double the angle, it'd be 4 theta, not 2 theta. Okay. We're almost done. This is our last, I think this is our last one. Oh no, we still have to do arc length, sorry. I know. I feel you. Find the area between two curves. So it says find the area inside r equals 3 sine theta and outside r equals 1 plus sine theta. R equals 1 plus sine theta. Wasn't that cardioid? R equals 3 sine theta. I actually have the graph here for us, so we don't have to worry about the graph. There it is. So this one is r equals 1 plus sine theta, and this red one is r equals 3 sine theta. There's a problem that I have in my Cal 3 class where we take a sphere, right? And we take the sphere, so imagine we have a sphere, 3-dimensional, and we take a drill, right? So let's say the radius of this is, let's say 4, okay? Radius. and we take a drill, and we're going to drill, and the drill bit that we're going to use, here's my drill bit. Okay, that's my drill bit. It has a radius of 1. Okay? And we're going to drill down the North Pole, out the South, and take out some stuff, right? And then I could ask you what the volume is, right? That would be hard enough. But what if I offset the drill? Instead of going down the center, I went down and just ran like tangent to the center line. So imagine I'm looking straight down on the sphere. Instead of drilling right down the center, I offset my drill bit like this. And I come in like that, and I pop out the stuff in there. What's the volume of what's left? Believe it or not, this red curve right here would help you solve that problem, because it's a polar region and it's offset off the origin. You see how it's offset? And that's how we would do it in Cal 3. I just was thinking about that as I was looking at it. Like, what would you do with that? Like, ever. But you could do something like that. So you can get like volumes of very strange shapes using things like this. How in the world am I going to do this? I want the volume, not the volume, the area of the region between them. That stuff right there. Outside the blue one and inside the red one. Any ideas? What's that? Okay, well, yeah, we could try something like that, but these aren't functions of x, are they?
Find where they intersect and subtract.
Okay, so if we look at where the two intersect, right? Then it's kind of like, here's your angle, right? If I could figure out the angle here, right? If I could figure out that angle and then figure out this angle, then let's just look at the red one. Here's out to that intersection point, here's out to that intersection point, and then the red one would go like this, wouldn't it? Like that? I could find the volume of that. Because, or not, I keep on saying volume now. I could find the area of that because I have a formula for it. It'd be 1/2, or integral, that 1/2 can come out. It'd be from wherever this angle started, right? Which we call, let's say, A, and then to where the angle ended, which we could call B, and then it would be just the radius squared d theta. And that would give me the area of the entire thing, wouldn't it? Like that? But then I could come in and do the same thing for the blue one, right? And the blue one would be inside, and it would be this, and I'd be able to find the area of that one. And then I just subtract the two. Got it? But I need to find their intersection. Right? I need to find the angle that would give us their intersection point. Set them equal to each other. That's what we've always done, right? Okay. Everyone understand what we're going to do? All right. And bring the functions up here. So first, intersection. Let's find their intersection. So set them equal to each other. So 3 sine theta equals 1 plus sine theta. This is going to be pretty straightforward, right? Subtract sine theta. You get 2 sine theta equals 1. Sine theta is 1/2. And then, we did that earlier, right? Sine theta is 1/2 is here and here. So pi over 6 and 5 pi over 6. Okay? Questions? So here we go. I'm going to do the integral from pi over 6, from pi over 6 to 5 pi over 6 of 1/2 times, now the outer one first. So let's find the outer one. The outer one was the 3 sine theta, but I need to square it, don't I? 3 sine theta, but then squared, and then d theta. That's going to give me the area of that outer one. And then I subtract from that the integral from pi over 6 to 5 pi over 6 of 1/2, but this time the inner one, 1 plus sine theta squared d theta. And both of those can be done with relative ease. This one, square it, right? It's a sine squared, power reduce. This one you'd have to FOIL it out. And you would get like 1 plus 2 sine theta plus sine squared theta. And you could integrate each one term by term. And then when you got to the sine squared, you would have to power reduce again. This is not like trivial, but it's not difficult either. We could do that. So, last topic. That's it for areas. There's a kind of a famous problem where you have a circular, like, I don't know, maybe like some sort of silo, like a water tower or something sitting there in a field, and you've got this rope, and you've got some animal, like a sheep or something, I don't know, a horse, tethered to this rope. And let's say the radius of this thing is, let's say 30 feet. And let's say you have a 40-foot rope that horse is tethered to, right? What's the grazing area of that horse? How much area can that horse graze in? You kind of understand what I'm asking? So if the horse walks all the way out straight, then the furthest it would be able to go would be 40 feet, right? Like that. And it could actually swing through an arc, and it could graze that whole area, couldn't it? And then it could swing down like this and graze that whole area. So that's half a circle. And we would know that pretty easily because we know that this is 40 feet, right? So this is like a radius, and you could find half the area of that circle. Where it becomes difficult is when it starts to walk over here, because the rope must wrap around this thing, right? So as it walks over, it actually starts to go like this. And then this one starts to go in like that. And these aren't like perfect circles anymore. But you can do this with polar equations. You can find this. You would never want to try this with Cartesian. This would be a disaster in Cartesian. We're not going to do this problem. But you can kind of see from that like why it would be preferable. All right, arc length, last one. If you're trying to find the length of a polar curve, the formula is, length is integral a to b, square root. I'm not going to derive this formula. I'm just giving it to you. dr. I think I had made a typo on this. Please check on Canvas. If you download this later, I think I accidentally put t theta or something here. It should be dr d theta. What's that?
R theta.
It says r theta? Yeah. So, it says r theta right here? Yeah, it should say d theta. Dr d theta. So what you're going to do to find the arc length is take the square root of the function squared plus the derivative of the function squared d theta. Now, I could do that one right there, but this is done in the book. And what they do is they set up the whole oh, let's do it. Let's not be lazy. All right, if I want to draw this cardioid, right? It starts here, it draws it. Do y'all remember how long it took to draw the whole thing? Like what the interval was? It was 2 pi for this one, right? So if I want to know the length of that cardioid, I would do integral 0 to 2 pi, square root, and then I have to take the function squared. The function here is 1 plus sine theta. So I've got to go 1 plus sine theta here, square it, plus now I have to square the derivative. The derivative of it is cosine theta squared, and then d theta. And this does clean up a little bit, but you'll get to a point where you can't do it. You can't do it by hand. Even a power series wouldn't work, and the book says use like a computer system to get the integral. But I just wanted to illustrate like how it's done. In the homework assignment for this, I have yet to do the homework for this yet. So there are, I think, 2 problems that I ask you to do, and I will take them all the way. And there'll be problems you can integrate. But that just gives you a feel for how the formula works. I was curious, could we verify the circumference of a circle? What is the circumference of a circle? We all know it's what? 2 pi r, right? So if I take the equation of a circle again, oh, this is going to be kind of awesome. Okay, what's the arc length of a circle of radius r? What's the arc length? Go all the way around. It should be 2 pi r, right? Let's do it in this formula. This should be integral from 0 to 2 pi, because I'm drawing the whole circle, square root of the function squared, which is just capital R squared, plus what's the derivative of the function? R is a constant. 0, right? D theta. What's the square root of R squared? R. So this is just integral 0 to 2 pi. Square root of R squared we said was R. But that's a constant, right? Pull it out. So I have 1 d theta, don't I? Antiderivative of 1 is theta. Go from 0 to 2 pi, and you get 2 pi r. That's pretty awesome. All right, we're done. We are done. Let me hand out what I have for you in terms of the final. You made it. Congratulations. All right, I'm going to stop recording because everything I talk about now is kind of irrelevant.